So this is the triangle they asked you to do in number 5 in the homework. And then in the homework, they asked you to dilate it, to enlarge it. That means dilate it. About the origin by a factor of 2. So our center of dilation is the origin. So we didn't talk about this yesterday, but what is going to end up happening to A when we dilate it? It's going to stay in the same spot. And we saw that happen too when we were doing rotations, right? Hey, Cole, that's 2. I wouldn't put it in your pocket because number 3 is going to be a paper bag and a write-up. I'd do a smart thing and stick it in your bag. Thank you. Remember with rotations, if a point was at the center of rotation, it didn't move either, right? Remember when we did reflections, if a point was right on the line of reflections, it didn't move. So same idea here. This is our center of dilation. Nothing at the center is going to move. So A prime is going to be right at the same location that A was. B and C are going to move because they're not at the center of dilation. Let's do B first. Remember to do this, and if you were absent last time, we'll want to pay close attention. Think about how to give directions to get from A to B. I'd say to get from A to B, you go up 4 and over 3. Up 4 and over 3. When I do my dilation, I want to do that same thing, but times whatever my scale factor is. We're doing a scale factor of 2. So instead of going up 4, I'm going to go 8. Instead of going over 3, I'm going to go over by 6. All right, so instead of going up 4, I'm going to count up 8. Instead of going over 3, I'm going to count over 6. And that gets me to right here. This is going to be my B prime. Same idea with C. We always count from A. We say, how far is it from A to C, or how do I get there? I go to the right by 3. I'm just going to double that. Instead of going by 3, I'm going to go 3 times 2. That's 6. That's going to get me here, and here's C prime. So there's my new triangle. Kind of overlaps a little bit with the original one. And since it's a scale factor of 2, it should be twice as big. So I need to get some input from you guys on this format. So on the warm-up, we're now working on number 11. Part A, they asked us which side corresponds to CB and which side corresponds to AB. What do you guys put for that? Anybody want to be brave and volunteer? Jackson, what did you put for CB? Yeah, C prime, B prime. So the original CB was this vertical line here. When I look at my new triangle, the vertical line is B prime, C prime. So using that same idea, think about what's going to correspond to AB. What do you think? A prime, B prime. All right, part B asks us to observe any relationships between the original sides and the new sides. So look at BC and B prime, C prime, and what do you notice about those two things? Someone give me one observation. I'm noticing like, I'm kind of seeing 2 different things. Give me one observation about A prime, B prime. I'm sorry, about BC and B prime, C prime. Nothing? Melissa, what are you noticing? They line up, like heading the same direction. Like if we were to extend them, they're never going to intersect each other. Can you remember the name of that? Starts with a P. They're parallel. Okay, great. Yeah. So BC and B prime, C prime. Oops, I'm calling it C prime, B prime apparently. Because I flipped them. That's the same thing. They are parallel to each other. That little, this is not the number 11. That's a symbol for parallel. Thank you, Alyssa. Somebody else want to tell me about the lengths? What's special about the lengths for BC and B prime, C prime? What's the relationship? They're not the same. They're doubled. Yeah. B prime, C prime is 2 times as long. Is that true for example, A prime, B prime? Does it look like A prime, B prime is twice as long as AB? Yeah, it does. And AC also? Yep, sure is. Part C is kind of a tough question. I'm curious if anybody has any insight on this one. The book noticed that AB ended up right on side A prime, B prime. They overlap each other. Same thing with AC. AC ended up on A prime, C prime. However, the third side did not end up on top of its original. And their question is why? What's different about the third side than the other two sides? Two of the sides end up right overlapping the originals, but the third one does not. What do you think?
Because we're starting at the origin,
Mm-hmm. It's really hard to put it in words, isn't it?
we started at the origin, the AB and AC are going to overlap because this side is not going to the side that's this side.
This side, yeah.
That side is not going to overlap because it's scaled at the origin, and so there's going to really overlap. Like
I got it.
It wouldn't scale properly if it were to overlap.
Correct. Okay. I think the keyword is this. You said it several times. Is the origin. The keyword is the origin. So I'm pretty sure that if I drew any line that goes through the origin, that when I scale it, it's going to end up on top of itself, right? Because we're scaling about the origin. But if our original line doesn't go through the origin, then it's not going to end up on top of itself. I think that's the kind of key piece to it. And you were saying pretty much the same thing in different words. Yeah, good. So however you want to put that, BC doesn't go through the origin. That's how I would say it. For D, says, could you get the new side lengths by just adding the same amount to each side? So in the original problem, they asked you to figure out how long the original sides were, and that was easy for the 3 and the 4. You should have found that this was 5 in the original problem using Pythagorean theorem. Okay, that was part of the homework assignment. And then once you get to your new triangle, instead of 3, now it's 6. And instead of 4, now it's 8. Instead of 5, again, you could use the Pythagorean theorem, or you could probably just predict since it's twice as big that it's going to be 10. The question they're asking in D is, can you just add the same amount to each side? Like if I just took this 3 and added another 3 on, that would give me a 6. That would work, right? But if I took the 4 and added a 3 on, I would get 7 and not 8. So that does not work. So I'd say adding does not work. Adding the same thing does not work. We must multiply. we can multiply each of those original sides by 2 and get the new sides. That does work. Adding's not going to work for us. All right, last question. I'm going to paraphrase this. So Monica made a new triangle based off of our same original triangle, okay? But Monica's new triangle has an A, she called it A triple prime, B triple prime. So the blue was the original, the red was the one that we made. She made a new one where A triple prime, B triple prime, or double prime, I guess it was 20 units long. Well, ours was only 10 units long, hers was 20 units long. And the original was 5 units long. The question is, how many times larger is her side than the original side? 20 is how many times larger than 5? 4, right? They're saying that 20 is 4 times larger than 5. So 4 is kind of our multiplier. So if I asked you how long B double prime C double prime was, would you be able to find it? How long was the original BC? The original BC was 4. We said our multiplier was 4. So what are we going to get when we enlarge it by a factor of 4? So yes, we'll go 4 times 4 to get 16. Okay, that was our warm up. Any questions on that before we move on? All right, we're going to introduce some new vocabulary today. You may have heard some of this before. We created 2 triangles in chapter or number 5. These 2 triangles are not congruent. Can we agree that they are not congruent? Congruent things have the same size and the same shape. These do not have the same size. However, they do have the same shape. So these are not congruent, but there is a word that describes 2 things with the exact same shape, but not necessarily same size. This starts with an S. Is anybody aware of the name of that? Similar. Yeah. And that was on our learning targets for today. So these 2 triangles are similar, but they are not congruent. We're going to practice making some similar figures right now. Go ahead and label on your notes right now. I'll have you do some of this on your own. But let's draw the original together. Number 13 in the picture, and you're allowed grid paper for this. I gave you a handout a couple days ago that had grid paper on the back. So get your craft paper out or get that handout out. You should have space on that, I'm hoping. And we want to draw that C that we see on number 13. So go ahead and make that happen. Count it out. Make sure you're getting everything the right size. If you don't have any graph paper, there is my extra copy tray is up there, and I copied a whole bunch of stuff that had graph paper on the back. So you can go through there and see if you can find something that's graph paper on the back. You might actually have more luck on the stack see the stack that's sitting on the bookshelf a little bit right there. Yeah. In there, I bet you'll find a bunch of stuff with graph paper. Oh, look at you, like right on top. Nice. Okay, we're not going to dilate this. It says to enlarge it, so we don't need to worry about a center of dilation. We want to make, I'm just going to do a couple of these. Let's make one with that's enlarged by 2. So can you draw me that same shape, but it's enlarged by 2? So if I were doing this, I would notice that the top of my C shape here is 6 units wide. So I'm gonna have to double, I'm gonna have to make it 12 units wide. Instead of going down 2 here, I'm gonna go down 4 here. You get the idea? Instead of going over 4 here, I'm gonna go over 8 here. All right, and then let's make a third one that's enlarged by 1/2. So this is from the original. We want it to be enlarged by 1/2. So is that actually going to be bigger or smaller if we're enlarging by 1/2? It's going to be smaller. Scale factor or a factor is going to be 1/2. So everything's going to be 1/2 as big. So instead of it being 4 units, or sorry, 6 units wide, it's going to be 1/2 6 units wide. It's only going to be 3 units wide. Instead of going down 2 here, I'm only going to go down 1 here. So big question, are these figures similar? They're certainly not congruent because they're all different shapes, but are they all similar? They're different sizes, but are they all the same shape? They are all the same shape. So yes, they are all similar. And I want to talk about, this is kind of the big important thing for today, okay? So please make sure you're paying attention, don't miss this. I want to talk about one of the key defining things for similarity, okay? I'm going to focus on these two figures right here. And I'm just going to mark how some dimensions on them. For example, the top edge of this was 6 and the top edge of this was 12. If I look at the ratio of the tops, a ratio just means to create a fraction, basically. The ratio of the tops would be, and I'm going to go the second one over the first one. So I'm going to be consistent about that because we're going to use some other slides here. So I'm always going to do my new dimension over my old dimension. So the ratio of the top is 12 over 6. And does that simplify 12 over 6? What does 12 over 6 simplify to? 2. Is that a phone? Yeah, it is. Put it away. Thank you. 2 over 1 or just 2? I'm going to look at this inner dimension. These are all 4s here, right? This is 4 and 4 and 4. And on my new one, it's 8 and 8 and 8. Agreed? So I'm going to call that my inner ratio. What would my inner ratio be? We'll send a note from the office. This could be it right now. That's not how it works. She calls the office, tells them that you're leaving. They'll send a note down. You want to go down to the school nurse now, and then she can check you out. Yeah, go. Just make sure that you, Valen, just make sure that you check out with the tenants. Don't leave without checking out, or they're going to mark you absent for the rest of the day. Okay. All right, my inner ratio, if I do it the same way, we want the new one divided by the old one, so 8/4. And what does that ratio end up equaling? That's also 2/1, right? And this is kind of the key thing. So when we do a dilation, we talk about similar figures, the angles all stay the same, but the side lengths change. The side lengths change, but the ratio between the original and the new side should be the same for every side. The ratio has to be consistent, or else the figures are not similar. The ratio has to be consistent. Okay. Any questions up to here? All right, so I'm going to go a little bit off script here. Can I get you guys to draw me a rectangle? This is not in the book. We're going to go a little bit off script here. It's okay. Don't worry. You got this. Draw me a rectangle. This doesn't need to be on grid paper. It can be, but it doesn't need to be. I'm going to tell you that this side is 8. This side is 12. And then I've got another rectangle next to it that's a little bit smaller. This side here is 6. This side here is 9. All right. Are they similar? Are they the exact same shape? Now they're both rectangles, but is every rectangle the exact same shape as every other rectangle? No, we can make like a super long and skinny rectangle, or kind of like a rectangle that almost looks like a square. Actually, a square is a rectangle. So are they similar? The only way for us to know for sure if they're similar is for us to do ratios. Okay, so let's start with the ratios on the side. So I'm going to make a fraction. I'm going to do my new shape divided by my old shape. So 6/8. And I'll reduce that as much as I can. 6/8, those can both be divided by 2. So 3/4. Can you go ahead and do a bottom ratio for me? Now, if the bottom ratio also ends up being 3/4, then the answer is yes, we're similar. Uh, 9/12. 9/12 is not 3/4, but is it the same as 3/4? Divide by 3. Divide by 3 will give me 3. Divide by 3 will give me 4. Ah, yes, it is. So are these two rectangles similar? They are. Draw me another rectangle down here. It's a little bit bigger than the original one. This one is 10. over 16. Is this one similar to these original ones? Let's compare these two and see if they are similar. If I go the side ratio, that would be 8/10, which we already, oh no, we haven't done 8/10 yet, have we? I'm sorry, that wouldn't be 8/10 the way I've been doing it. Let me be consistent here. I flipped it around, didn't I? It would be 10/8. 10/8 is the same as 5/4. Does the bottom ratio also come out to be 5/4? The bottom ratio would be 16/12. Reducing 16/12. Those are both divisible by 4. That'd be 4/3. So we know that these two are similar because the ratios are the same. We know that these two are not similar. You get the idea of similarity? The ratios have to be the same. So you compare the two sides that are matching sides, make a fraction. If it reduces to the same thing as all the others, then you've got a similar figure. Otherwise, it's not. All right, we're gonna do one more problem here. You guys got this. You're gonna love this. This is number 16 out of your book. So we're going back on script here. We got two shapes. I'm gonna go ahead and draw them. They kind of look like, I don't know, like flags, sort of. Like weird medieval pennants. This is part B, by the way. We're skipping part A. This one's got an 8, an 11, and Y. This one's got a 24, an 18, and an X. We're going to use the fact that we just established here to solve for X and Y. Okay. So I want you to, off to the side here, write me a ratio that's got X in it. Write me the ratio that would have X in it. We're going to assume this is our new one. So X should go on the top of this ratio. What should go on the bottom of it? 11 matches up with X, right? So we'll put 11 down there. That's our corresponding one. You get this down? Right next to that, I want you to write me another ratio, but the other ratio should not have a Y in it. I do not want a Y in this next ratio. Can you find me some other things I can put on the top and bottom? I want two numbers that I can put on the top and bottom of this one. I do not want a Y in there. What two numbers could I put in the top and bottom of this second ratio? We could put the 8 and 24 in there. Those are matching sides. Now let's be consistent. I put the X on the top here, so I'm going to put the 24 on the top there, right? The bigger one on the top. So 24 and 8, well done. And what do we know? If these two things are going to be similar, what do we know about these two ratios? They should reduce down to the same thing. They should be the same thing. Put an equal sign in between. That's how we say something's the same. We've now written an equation that we can solve for X. We don't know what X is right now, but we're going to figure it out here pretty quickly. Now, the reason I wanted you to write the second ratio without a Y is because if I have an equation with both X and Y, I can't solve it. I need to make an equation that only has one variable in it. So that's why I was trying to avoid the Y a moment ago. So let's solve this. You guys solved a bunch of these in your homework. Cross multiply. 8 times X is 8X. 11 times 24 is, someone got a calculator out? We can wait. Dun, dun, dun. 264. Which I'm curious if that's going to divide by 8. It should, because it divides by 24 and 24 divides by 8. I'm going to guess it's 33. 33? Cool. We found that x is 33. Can you guys set me up another equation? I'm going to get you started on this one. I want this one to have y. I want to get y into this left-hand one. Now, to be consistent with what I've been doing, I'm going to put the 18 on top and the y on the bottom. Could you finish up that equation? Could you give me a couple numbers in the second fraction and solve that? By the way, there's no reason you can't use some of the same numbers that we used a moment ago. We definitely don't want to introduce any more variables over here. So what numbers are you going to put into your second equation? We need another matching pair of sides. 18 and y we used to get that fraction. Which two sides are you going to use to get this fraction? Brady, what do you want for the second fraction? You want to go with the same thing you gave us last time?
Yep.
24 and 8? You totally can. Did you guys use 24 and 8? 24 and 8 works. What would be the other option? We could do 11 and 33. You said technically, are you hesitating to do that? I would, especially if this were a test, because why? We didn't really check our work for this, right? We think this is right. We think this is the right number, but we could have made a mistake, right? Probably safer to use something. I don't have to worry about a mistake in the 24 and 8. Those came from the original problem. I'm going to go with the ones from the problem if I can. Okay, go ahead and cross multiply and solve that. 24 times y is 24y, and 18 times 8. I don't know what that is. 18 times 9, 72, 144. Thank you. 44. And that does divide by 24. I think that's 6, isn't it? Can anybody think of a way that we could check this? I was really firm last week when we were working on the checkpoint problems. You guys check your answers. How do we check your answers here? Yeah, we could put it back into the ratio equation. We could put it back into the picture too. I'm going to start with the picture. Oftentimes, if I put it back into the picture, that's easier for me than going back into the equations. And I think I can see that this is correct. Randy, really? I thought you put it in your bag. All right, paper bag incoming. Let me finish this up. We had the 8 and the 24 to begin with, right? How much bigger is 24 than 8?
3 times.
It's 3 times as big. 8 times 3 is 24. Is that holding true with the 11, the answer I got for x also? 11 times 3 is 33. What about the 6 I got for y going over to this 18? Does that work also? Oh, I think that we did it right then. Yeah, I think we've confirmed it. Okay. So here's what I want you guys to do right now. I want us to start our learning log on similarity. Is there a learning log on similarity? Yes. Okay, this is our similarity graphic organizer. And I want you to start thinking about 2 pieces of this right now. We're not going to do this all at once because we're going to spend the entire chapter talking about similarity. But there's two parts of this that I think we can start to answer. Now, if I were writing notes in here, I probably wouldn't fill the whole space because we might see some more. We might see some more information that might be helpful to us there. But right now, how can I tell that two figures are similar? If you want to go back to the example that I kind of made up with the rectangles, remember we were able to determine that these were similar and these were not similar. So if you understood that example, then either write something about that example here or maybe copy the example itself into here. Okay, so what does it take for two things to be similar? The main thing that we learned today was that the ratios have to be the same. All of the ratios have to be the same. And then this is how can I use what I know about similar figures to solve problems? That's what we did right here. We knew that the figures were similar, so we set up some ratios and made an equation and solved it. So write yourself some notes or write some examples in there. When you're done with that, you've got the rest of the period to be working on homework. I'll go ahead and put the homework assignments up here. With our remaining time, if anybody has any questions from the previous homework, please get my attention. I'd be happy to go over those with you. Yeah. Oh, yes, because you were, I will come around.